Okay. Okay. All right, so welcome to class. Today is the last meeting of the lecture portion of the course, and so today what we're going to do is do the review sheet and talk about it. Talk about what the format of the test is going to be, what's going to be on the test, and then for that probably won't take the whole time. For Thursday, what I had planned was to go over the final projects, and we should have plenty of time to do that. If anybody wants to, once we finish the review session, if anybody wants to go first, they're more than welcome to present today. But if you want to wait till Thursday, that's fine. So the presentations will just be short, little 5 to 10 minute presentations. Just show off what you did. But we'll do that. We'll do that on Thursday, unless anybody wants to do that after the lecture. I mean, not the lecture, the review session. So if you go to, I am still recording this, by the way. So if any of you don't, I'm about to say, if any of you aren't here, that wouldn't make a lot of sense. But if any of you know somebody who's not here, they can go back and look at this video as well as look at the review sheet itself. Okay. So if you go to other material, you'll find the final exam guide, final exam study guide right here. And I'll go ahead and open that up. The syllabus open there for a second. That's kind of good. I'll close this up. Let's look at the syllabus here real quick, because it kind of has to do with the there. All right, so we're right here on April 28th. I was gone last week. Hopefully everybody got that message. I seem to have picked up something in Chicago, because I'm kind of dragging. Maybe it was just the there's not really a time difference, but maybe it's just the sometimes when you travel. All right, so I was traveling last week. This week's April 28th, the review session, and then on that's for the whole week. So on the Friday, we'll do the final project presentations. That's where we have that listed. So the test is basically going to be on the second half of the course. Now, one thing that we did was surface flow. We compressed surface flow into the first portion of the course, which was okay because it went really well with terrain and surface analysis. And so we covered that actually in the first part of the first exam. We covered it really well. So really the second exam is only going to cover these last 4 lectures here. Okay, so that's what we're talking about from March 24th to April 14th. Okay. Now, having said that, if you go look at the review sheet, I do say that although this exam will be heavily weighted toward the second half of the course, really those last 4 lectures is what I'm talking about when I say that, there will be some basic raster operation type questions as there were on the last exam. Okay. So just a few of those. Basically, those are review. They're fundamental to understanding a lot of the other problems that we try to solve in this course, and so I think it's important that those items be tested. Okay, so doing basic operations. What do I mean by that? Some sort of basic math operation you should expect to see on there. Some sort of conditional operation will definitely be on there. What won't be on there this time is we had a scenario where you actually had to do a weighted overlay on the last exam, and we tested that in the first exam sufficiently. So that won't be on there, but some of the basic operations. All right, including, so I said conditional, some sort of basic math operation, some sort of focal operation, not very complicated. We're not going to calculate slope or anything, and some sort of zonal operation. So you can expect a question on each of those on the exam. All right, so those will really be the only repeat items, and they won't be the exact same questions. For the most part, it will cover the content of those last four talks that we had, and the concepts that we discussed in the exams. The format of the exam will be very, very, very similar, really the same. I mean, the questions won't be the same, but you'll have short answers, working out little problems, and then you will have a diagramming question, like you did on the last exam. And that was one where I think most people struggled. So we can go through some of the potential diagramming type questions here as we go through this review sheet. So let's talk about just go through the course content chronologically and review some of the items that you should study for. So we spent some time talking about spatial interpolation, and I want you to be able to articulate what spatial interpolation is, why is it done, and so for that we're basically looking for, particularly for this class where we're talking about GIS modeling and raster, we're basically creating an evenly spaced grid of values from a set of sampled locations or known locations, whatever you want to call them. So we have that set of known values at certain locations, and we're trying to create a evenly spaced grid of values where we're basically taking a guess using math. We're approximating the value using some sort of mathematical function. And there we talked about a number of different mathematical functions. One thing that's important to remember is that interpolation implies that we're trying to find the value of unknown locations or unsampled locations that are spatially within the sampled points. So if we go outside those, in other words, if I had a bunch of temperature values in Forest County, it technically wouldn't be interpolation to derive a value in Lamar County using those values, because that's outside of the sampled locations. All right, why is spatial interpolation done? Because oftentimes we can't know the value everywhere. We're trying to create a smooth surface, and on top of that, when we do raster modeling, lots of times it's important that we have a kind of wall-to-wall surface of values. And because we can't sample everywhere, we need to do spatial interpolation to create that map of values. We're creating a map of values. All right, we categorize spatial interpolation in a few different ways. So you should know what these terms mean. Talked about a spatial interpolation being being global or local, and then exact versus inexact. And just to review those terms really quick, a global interpolation technique uses all of the data to predict the value at a certain location. A local technique uses only the nearby points, and lots of times you define what nearby means, but we're not using all of the points. So it's the difference between a global and a local spatial interpolation technique. Exact versus inexact. A exact interpolator will give you the value of a known point on the predicted surface at that location. Okay. So let's say I have a bunch of temperature points, and if you can imagine in your mind a grid cell overlaying those temperature points, some grid cells won't have points in them. Okay. Some will have points in them. When we predict values for every cell center, the cells without points in them, we're doing interpolation, and we're coming up with a new value. The cells with points in them, where there's a cell center with a point in it, if the point after the interpolation is run, if the value of the point is the same as the value, excuse me, the value in the interpolation that the interpolation produced, then it can be said to be an exact interpolator. If that's not the case, if the interpolation algorithm produces a different result, then it would be an inexact interpolator. So trend surface is the classic example of an inexact operator, interpolator. So it produces a trend surface through a series of points, and doesn't necessarily worry about making the surface pass exactly through every point. Most interpolators that we utilized in this course are exact interpolators. And really, when we're trying to create a surface for the purpose of using that surface for water flow or temperature, that's usually the best thing to do. So you have exact interpolators are very common, where inexact interpolators are mostly used for looking at trends rather than trying to approximate the surface. So IDW is an exact interpolator. Here we've got some listed here. Nearest neighbor would be an exact interpolator. Trend surface would not. Spline is an unusual case because depending on the parameters, it can be an exact interpolator or it cannot be an exact interpolator. It basically uses local trends, and you can tell spline to force it to go through the points, or you can tell it to be off by a certain amount, in which case it wouldn't be an exact interpolator. All right, you should know in general how each of these interpolators operates and kind of what categories they fall into in the above list. It's all included in the slideshow. I just mentioned most of it. So, in the PowerPoint. For this exam, you will have to calculate IDW. Okay, so that IDW I didn't mark on there. the only one you'll actually have to calculate. So you'll be given a cell center, and the distance to one or more points, probably be 3 or 4 points, and you'll have to calculate what the value is at that location given certain input parameters. So study that that slide. We actually went over 2 different ways that you can calculate those. So whichever way works best in your mind, commit to memory and be ready to reproduce that on the exam. All right, now Kriging was a special case. We took 2 weeks to do interpolation, and we spent one week just on Kriging. And so you may be asking, what do I need to know for Kriging for the exam? Well, not everything. It was a fairly involved lecture, but you do need to understand that Kriging is a geostatistical method for interpolation that utilizes information about 2 things. So it utilizes the general trend, and it also looks at local variability. Particularly, you should be able to talk about or understand what autocorrelation is. What is autocorrelation? It's particularly, I mean, I guess I say autocorrelation, but I mean spatial autocorrelation. What I mean there is that spatial autocorrelation is a measure of how much values are related that are close to one another. So are close values more related to a particular value than far values are? That's what spatial autocorrelation means. So if I can come up with a measure to quantify how closely related close points are, which is spatial autocorrelation, then I can use that in my prediction. So Kriging uses that information. It says, okay, if the values very close to me are highly correlated with my value, then I can place more emphasis on those points that are nearby me. And so what Kriging does is say it creates what we call the semivariogram, which allows us to plot autocorrelation. Okay. And that point at which the semivariogram kind of levels off, okay, we call that the range, gives the take-home message is that at that range, that distance, because that distance is a real distance, the ability to use points beyond that range for interpolation, it's not effective. It's not effective to use points beyond that range for interpolation. Okay, so you should be able to know that. You should know that. Okay, so all right. Okay, you should be able to identify and report examples of spatial problems, particularly the ones that we discussed in class. So we're moving. You know, the first part of the lecture, the first part of the class, we kind of went through a bunch of applications. You know, talked about hydrologic modeling. We talked about terrain modeling and that sort of thing. And in the second part of the class, we took a short break talking about interpolation, but then we got back into that same sort of flow. We talked about the big one that we talked about in the second half of the course was diffusion modeling. Okay. We talked about 2 different ways. We didn't spend as much time on cellular automata, and so there's not as many. The test doesn't focus on it as much, but it does ask a few questions that you could probably. I pulled this up. So, you probably get by on the questions by just going back and studying these slides on cellular automata. Okay, those slides. Okay. So it works by defining a neighborhood and then applying a function to that neighborhood. And that function is applied the same for every cell. So the growth of a particular cell is determined by some function of the neighborhood and some function of the value that's already in that cell. Okay? And it's a time step. Both of them are time steps. That's the type of modeling that we covered there. So when we got into diffusion modeling, we talked a little bit about the difference between expansion diffusion and relocation diffusion. And we noted that we were basically going to talk about expansion diffusion, where we're coming in direct contact with the particular thing that we're trying to model. All right. I wrote the words capability, suitability on there because the modeling technique that we went over utilizes the same principles from capability, suitability modeling. In other words, instead of in capability, suitability modeling, the goal was to answer the question, could a particular thing exist at this location? And with diffusion modeling, we're saying, how quickly can a particular thing grow under various conditions? So it's the capability or suitability for growth. And then this is where we can kind of go ahead and diagram this process, okay? Because the next step was to use least cost distance modeling to actually implement that that task. So I'm going to pull back up the lecture here real quick as an example. So here's the lecture. Here's the diagram from the lecture. I'll go ahead and make this big. Okay. But you should understand what's going on here. So we've got the, because you're going to have to diagram this process, and I'll tell you on the test some things that could change. Okay. Some things that could be slightly different. But other than this will be the basic outline of how you would have to diagram it on the test. Okay. So let's start up here in the upper right-hand corner. So we've got, yeah, it's upper right-hand everywhere. We've got our factors that influence diffusion. So those are the main inputs to the model. So where this diagram may differ from what you'll have to diagram on the test is this part, this reclassify to movement rate. I may tell you, well, I will tell you on the exam, in order to calculate the diffusion rate, you have to multiply this input layer by something, or you might have to divide it by something, or you have to do some sort of operation to get from your factor influencing diffusion to a movement rate. So I'll describe that process, and you'll tell me what operations that you'll do to make that process work. From that point on, your diagram should look fairly similar to this. Okay. Once you have movement rate, which is distance per unit time, you should know that the next step is to basically divide 1 over the distance per unit time, which will give you time per unit distance. Time per unit distance. So this would be something like miles per hour would be ridiculous to be modeling, but it could be meters per month that we were modeling here. Okay. And when we divide it by 1, we're going to get months per meter. We're going to get that. We're going to get that value. Then, since it's a rate at that point, we can use that to find the cost distance. In other words, the output of the cost distance model is a value that tells us how much in terms of our cost, and our cost here now is in time, how much in terms of our time is going to take to get to every cell. And then we simply reclassify and say, Okay, well, the time step was 1 month. So anything where the cost was less than 1 month is where it got to. So then we have our new origin, and that loops back as part of the feedback back to the main portion of the model. Okay. Your origin is wherever the phenomenon that you're modeling starts. All right. So that's the process. This part here is where you might have, well, you will have a little bit of differences in your model, because this says reclassify to movement rate. This is simplified, so you'll expand this. This should look fairly the same. All right. Escape. All right. So make sure that you have a feedback loop. And then I did say this is one where you will diagram. Okay, so you diagram on the test. I put that right there in the review sheet. You'll also have, in addition to diagramming, you'll also have to answer a question on the importance of choosing a proper time step. For example, I might ask, what if I choose a time step that is too small? What happens? Well, it may be that there's no growth that occurs in that time step, and so no growth would ever occur in this model. If no growth occurs, the new origin isn't any different than the original origin, and so there's no the feedback doesn't change, and the growth never occurs. Okay. So the importance of choosing a proper time step that allows growth to actually occur within that time step. All right, so that's diffusion modeling. The next thing that we covered in the course was the calibration, verification, and validation. Okay, so you should know what each means. This one, although the Cellular Automata had a reading associated with it, I didn't have a reading associated with calibration, verification, and validation. And so you get most of what will be on the test from the slides themselves here. Okay, let's go back through the slides. Oops. And look at those definitions. Okay, let's go back here. We've got acceptability. Acceptability is a measure that's not necessarily a number. It's basically is the end user satisfied with the results? Is it acceptable? And sometimes that has more to do with being able to explain the result to the user. That has to do with making sure that the user finds that you can articulate the accuracy back to the user, and it's less concrete than these other items that are on here. Okay, accuracy is a measure of how well the model performed, and we can quantify that value, that accuracy value, in a few different ways. We talked about two primary ways to calculate accuracy. We talked about calculating percent accuracy, and we talked about calculating RMSE. And we did calculate percent accuracy in our in our labs. We didn't calculate RMSE, and I won't make you reproduce that on the exam, but we did talk about percent accuracy, and so there's a question that relates to that. All right, parameterization. Parameterization is the process of coming up with parameters for a model to use, and we did this with the kudzu model. That was our practice for parameterization. That's one way to do parameterization. Another way to do parameterization is to use a mathematical process like regression, and we only really demonstrated that. Okay, so parameterization is the process of arriving at parameters for a model to utilize, and sometimes that involves a building a model or using steps in a model. It's important that whenever you do parameterize a model, that you do not utilize the same data in your parameterization that you do for accuracy assessment. Okay, so you use one set of data for parameterization, another set of data for accuracy assessment. And the reason is because if you use a set of data for parameterization, it will, by its very nature, create an accurate surface. And so you need to withhold some data in order to truly calculate the accuracy for a data set. Okay. One way to kind of utilize the same sets of data is through a term called cross-validation. Cross-validation is where you do the validation process over and over and over again, but you hold out one or a few items from your original data set. Sometimes we call this bootstrapping. Okay. These are the slides that related to that. Yep. So right in through here, cross-validation. Leave one out or leave a percentage of your data out. It's an iterative process. But what you can do is calculate the error from running the validation step, I don't know, 100 times, where every time you leave a different one out. And this way you can kind of, you can use the same data because you left one of the data sets out, and it will help you to understand your accuracy even though you used less data overall. All right, the steps for verification. That's back here, actually. That was a little bit out of order, but this is what we're talking about here. Okay. So verification is the process by which you try to verify that your model is working as expected. You look for logical errors. You look for problems in the model that you've created. Is it working well? And so oftentimes you work a process out by hand, or you take it outside of Model Builder in the GIS world and do each step and verify that the output of the step is what you expected that to look like. Because it could be that your environment variable is set such that it's operating on a much smaller area than you thought it should be working on, or it's treating no data values different than you thought it should work on. So you work it out manually. That might mean mathematically by hand, or more often in the GIS world, it means running each of the tools individually and looking at the results, inspecting the results using the identify tool, and finding out if it works. So you compare the slow process to the GIS model that you worked out, and you find out if the results are the same. So that's verification. All right. So that is that's all we really covered in this the second part of the course. So I tried to basically take these terms right off the exam as it stands right now. The exam will be, I forgot to put the date. I usually put the date of the exam on the review sheet. So that's important. So it is a Thursday at 8 a.m., May 7th. Okay. May 7th. And I will be here really close to 8 a.m. I mean, it may not be exactly 8 a.m. I'm telling you, I may be five minutes late or so. Okay? So don't panic if I'm not here right at 8 o'clock in the morning. My wife will be out of town, and I'll be dropping my kids off for school, and that's what I usually do. I usually take my kids to school, but I usually get here about 8:05 because I pull in about 8 and park. So it might be the same. I'll try to drop them off a little bit earlier, but I just realized that when I looked at the date and the time that I might be 5 minutes late. And for the people on the coast, you don't have to come up here or anything. We'll have a proctor down there for the people on the coast. Are there any questions?
So the only calculation you said would be the IDW, plus there might be some older stuff from the previous kind of review from the previous exam. What calculations you really have to do?
Yeah, so there will be an IDW on there. There will be some calculations like the previous exam, but those will be very, very simple, straightforward. You shouldn't need a calculator. I don't mind if you use one, but you shouldn't need one. And then a percent accuracy type of a question. So looking at the overall accuracy of a data set where you're given, basically how many were accurate and how many weren't, which also should be fairly easy and straightforward. It's a great question. Any other questions? Are there any questions about what we're doing on Thursday? Thursday we'll talk about for this class. For a minute, I forget. I'm pretty sure that for this class I said everybody's still doing presentation, right? That was what's that?
I thought you said we weren't.
We aren't doing presentations? Did I say that?
You had said only graduate students.
Okay. Did I say that?
Yeah.
You guys aren't sure? Okay. I know I said that in my other class, only graduate students. What's that? Yeah, did I send that to you in an email?
Yeah.
Okay. So yeah, I had a mess up. Well, I messed up there. So both of you on the coast are undergraduates, right?
Yeah.
Yeah. How far along are you on your project?
I emailed you about it, and
Right.
pretty much told you that there is really nothing, not really a guideline or anything. So I'm not exactly sure where to start.
Okay. Yeah. In my response, yeah. All right. So yeah, we can talk. Let's talk outside of class. Yes, the presentation on Thursday is not a. We're not looking for anything big. Okay, you present your model, you present the output of the model, and then you should be done. Okay.
On Thursday?
Yeah, that's on Thursday. This is actually the last week of classes. So basically what I'm looking for is that you can use Model Builder to answer a question that you want. Let me look here. So you could modify a lab assignment. That would be a great final project. Okay, you do something like that.
Data?
What's
You
that?
you don't want us to change the data or anything? You can use the same data?
Well, you could use the same data if you want to, but you should modify the exactly what it does, and explain why you modified it, that sort of thing.
He wants to do a write-up or something.
A write-up of the project? Yeah. A write-up, a short write-up. Yeah, like less than a page. Graduate students, that's different. These are undergraduates. I'm sorry, I see your email, Kristen, and that I sent out on Monday. I responded to your question as if you were in the other class. So I do admit that I messed up. So if you don't feel that that you can have an assignment ready by Thursday, I'll give you some extra days and you can just present it to me. Okay. So I do realize that I messed up in my email and said that you didn't have to do it. It's my fault then. I wasn't feeling well coming back from Chicago, and yeah, you could see that in my email. I assumed that you were in the other class because I talked about branching and looping and statements and stuff like that. So it's my fault that I messed up. So yeah, additional guidelines. Really, I want this to be about the same level in terms of difficulty as a lab assignment. So you're creating a model, and by that I mean a model that uses Model Builder, that connects more than one tool. So that's one of the requirements, is it connects more than one tool, and that it produces an output that you can explain as useful. So it doesn't necessarily have to be useful to the whole world, but it's useful for your processes. And for this course, it has to be raster data. Okay. You can utilize some vector data, but you have to include some raster data in that process. Okay. So yeah, maybe what I'll do is with the Coast people, I'll meet with you guys separately to do a presentation. Okay. So because you might have relayed this information to the other people down there. Okay. So we'll just meet on Thursday. In fact, if you guys want to be here, I'll broadcast the screen, but I won't have you guys present on Thursday. We'll schedule a different time to talk about that, sometime before the end of the semester. So sometime early next week. Does that sound better?
Yeah.
Yeah. Okay. I'm sorry about the email. I was answering a few different emails from students that were all in the other course, and I was just on that track. So I do know that you're in this course, but I messed up. So now it's all on video. Okay. Any other questions? So we'll see everybody on Thursday. The Coast people will have the Hattiesburg people present. The Coast people will not have to present because of my mistake, and they can see what you all did, and maybe that'll help spurn some ideas. All right. Any other questions? Okay. All right. we'll end this, and that'll be that. You're fairly backlit. Is Bradley down there too? Yeah, okay, all right. I couldn't, because I know there's other students in the room, I can't see everybody. But Bradley, we have, I have your exam from the first half. That would be helpful to you. I can send it down via campus mail to, who would you prefer, like Holt or Carter? Do you see any of those guys more often than not?
Probably Carter.
Probably Carter. Okay. So I'll send it down to Carter, and I'll send an email to him and CC you and tell him that that you have it. You can pick it up from him. All right. Okay. I forgot to bring it down last time.